Here we're going to work through problem 8.62, which is an energy balance problem involving both a change in temperature and a change in phase. So in this problem, we have a liquid stream that contains 50 mole% benzene, and the balanced toluene at 25 degrees C is fed to a single stage evaporator at 1320 moles per second. The liquid and the vapor streams leave the evaporator are both at 95 degrees C, and it tells us the liquid contains 42.5 mole% and benzene, and the vapor 73.5 mole% benzene, and it asks us to calculate the heating rate for this process in kilowatts. So we can first start just by drawing and setting up the process. So again, this is problem 8.62. So here we have a single stage evaporator. So entering the evaporator, we have 1320 moles per second, and we're told this is 0.5 mole benzene per mole and 0.5 mole toluene per mole. And it enters at 25 degrees C. And the evaporator is operating at 95 degrees C because that's the temperature at which both streams exit. So we're asked to calculate the heating rate in kilowatts. So again, coming out of the system, we're going to have a vapor. We don't necessarily know what the flow rate is yet. So NV moles per second, and we're told it's 0.735 mole benzene per mole, and therefore it's 0.265 mole toluene per mole. And then we also have a liquid stream coming out, so I'll call this NL moles per second. And this stream, we're told, is 0.425 moles benzene per mole, and therefore 0.575 mole toluene per mole. All right, so this is the information that's given. So the first thing that we can do is we can use our material balance to solve for NV and NL, and we can do the total balance, which says 1320 equals NV plus NL. And then we can pick either the balance for benzene or toluene and solve that. And if we do that, we will end up getting NL equals 1001 mole per second, and then NV equals 319 moles per second. I'm not going to work through that. You can work through that as a practice. Okay, so for this process, we're asked to calculate the heating rate. So we can start with the energy balance, and the energy balance is going to be delta H plus delta EK plus delta EP. And we're going to assume that the change in potential and kinetic energy for this process are negligible because of the changes in temperature and the phase change. And that's going to equal Q plus shaft work, but there's no moving parts in this system. So we're going to take WS to be 0. So here we just need to calculate all of the delta H's for this process. And so we can do that two ways. We can set up an enthalpy table, or we can just calculate all of the individual delta H's that are occurring. So if we look at those delta H's, for this process, we have benzene, and I'm just going to call benzene as B. So benzene is going to go from a liquid at 25 degrees C to benzene as a liquid at 95 degrees C. And then we also have toluene that's for a liquid at 25 going to toluene as a liquid at 95 degrees C. So these are just going to be like a sensible heat change, like a CP delta T type calculation. And in these cases right here, we're going to need the CP of the liquid for each one of these. And I know I can get that in table B2 in the back of the book. The other delta H's that we're going to need is benzene as a liquid at 25 going to benzene as a vapor at 95 degrees C. And then also the same for toluene. Toluene as a liquid at 25 going to toluene as a vapor at 95 degrees C. So for these two processes here, we're going to need the heat capacity for the liquid. So we're going to have to heat up the liquid to the boiling point. So we're going to need to know the boiling point. And then at the boiling point, we're going to use the heat of vaporization for each one of them. So we're going to need the heat of vaporization. The boiling point and the heat of vaporization, we can get these from table B1. And then we're also going to need the CP of the vapor for each one of these, which we can get from table B2. All right, now let's go and set up our enthalpy table. So for our enthalpy table, what we're going to need is we're going to need the substance. And what we're going to have to do is we're going to have to account for each species in each phase. Then we're going to need to get the moles in of each one, the enthalpy in, the moles out of each one, and the enthalpy out. So what we're doing is effectively setting up a table of tabulated data so that we can do our energy balance as Q equals delta H, which is going to be the sum of N out, H out, minus the sum of N in, H in. Okay, so for our substances, we have benzene as a liquid, and we have benzene as a vapor, we have toluene as a liquid, and then we have toluene as a vapor. Our moles entering, we can look at the process up here, it's 50 mole percent each, so we have 660, and then these units right here are going to be moles per second, and then on the enthalpy, it's going to be kilojoules per mole. There's no vapor benzene coming in, there's 660 toluene entering, and then there's no toluene vapor entering. And then if we use our calculations, or if we use the NL and the mole fractions in the vapor and the mole fractions in the liquid, we can calculate the moles exiting of each one of these species. So benzene as a liquid exiting is going to be 425, and then the same moles per second. Benzene as a vapor exiting is going to be 234. Benzene or toluene as a liquid exiting is 576, and then toluene as a vapor exiting is about 85 moles per second. Also, what we need in our for our enthalpy tables, we need to define a reference state. So these are going to be the state to which we define all of these enthalpy values that we enter into the table. So generally what I like to do is define the lowest enthalpy condition, or whatever is most convenient. So in this case right here, the stream with the lowest enthalpy is going to be the stream entering, which is the liquid at 25 degrees C. And both species are at the same temperature entering, so that's what I'm going to set the reference to. The reference state doesn't have to be the same for different species if there's no reaction occurring. So here we're going to say the reference state is benzene and toluene at 25 degrees C as a liquid. And so in these cases right here, the enthalpy of these at this state is going to be equal to 0, because that's what it means for our enthalpy, for our reference state. So because the stream entering, both of these streams are at 25 degrees C and the outstreams are at 95 degrees C. So I'm just going to make that note on my table. So the enthalpy of benzene as a liquid, toluene as a liquid are set to be 0. So if we look now up at our energy balance shown up here, this term right here, the sum of the Ni in Hi in is going to be 0. So what we need to do now is we need to go ahead and calculate all of these values, and then we can go ahead and calculate our Q by just the sum of the moles times H out. All right, so let's do this. Actually, so what I want to do is for every unknown enthalpy, I'm just going to give them a label. So H1, H2, H3, H4. Okay, so again, we know how to calculate delta H. So delta H for a change in temperature is going to be integral of Cp dt from T1 to T2. In this case, for benzene as a liquid, from T1 to T2 is going to go from 25 to 95 degrees C. And again, and this is going to be equal to our delta H is H1 minus H reference, which remember this H reference we set to 0. All right, so we can get the Cp of benzene as a liquid from table B2. And if we go to table B2, we're going to see that that value for benzene as a liquid is going to be 0.1265 kilojoules per mole, degree C. Okay, so what I did is, there is another term, but for the heat capacity of a liquid, I'm going to assume it's fairly constant with respect to temperature. So I'm going to drop the temperature dependent term. That can be a reasonable assumption. Here we have a fairly large temperature change of 70 degrees C. So I may lose a little bit of accuracy in my calculation, but I'm just going to do that here just for the sake of simplicity. So what that does is, because I have a constant heat capacity, my integral then here becomes delta H becomes Cp delta T. So in this case right here, my H1 equals 0.1265 times my delta T, which is 95 minus 25. And if I go through and calculate this, I get 8.855. What is it? Kilojoules per mole. Let me just write those a little bit more clearly. Okay. So I can also do the calculation. This calculation is going to be similar. Oops, let me. All right, I can write up here. So I got H1, 8.855. And again, these units are kilojoules per mole. I can do delta H. Let's see. I can do delta H3 similarly. This is going to be the integral of 25 to 95 of Cp of toluene as a liquid. This one appears benzene as a liquid, dt. And same as before, the H reference equals 0. So H3 here is going to be, I need to find the value for the heat capacity for toluene as a liquid from table B2. And if I look that up, it's 0.1488 kilojoules per mole degree C, or per K, same unit designation. All right, again, I dropped the temperature dependent term because I'm just going to assume the heat capacity of the liquid is fairly independent of temperature. Again, I may lose some accuracy for this. So here, wait a minute, okay. Let me go ahead and do this right. So it's again, the heat capacity, or the H3, it's going to be Cp delta T. So I have H3 equals Cp times 95 minus 25. And if I do that, I'm going to get 10.416 kilojoules per mole. So 10.416 kilojoules per mole. Okay, I got those two values. Now the next two, it's going to be a little bit more to it. All right, so I'm going to look at delta H2. And remember, this delta H2, delta H2 goes from benzene as a liquid at 25 to benzene as a vapor at 25. So what I need to know here first is the boiling point. So T boiling point of benzene, if I go to table B1, I find that that's 80.1 degrees C. And while I'm here, I'm also going to get the boiling point of toluene. So from the table, it's 110.62 degrees C. And also, I'm going to need the heat of vaporization of benzene. Delta H vape of benzene is 30.765. And this is going to be kilojoules per mole. And then delta H vaporization of toluene equals, what is that? I can't really read my writing there. So I'm going to go to the table B1, and I'm going to see that the heat of vaporization for toluene is 33.47. Kilojoules per mole. Okay, so what I'm going to do now is, in order to calculate my delta H2, I have to go through a process path where I first have to heat up the liquid to the boiling point. So that's going to be an integral of 25 to 80.1, because again, that's the boiling point of toluene, or I'm sorry, of benzene. So we're looking at benzene right here. So this is going to be integral 25 to 80.1 of Cp benzene as a liquid dt. And then I'm going to have to vaporize the benzene. So that's going to be a plus the heat of vaporization for benzene. And this is at 80 degrees C. Plus I need to do the integral from the boiling point up to the final exit temperature of CP benzene as a vapor dt. And so in order to do that, what I need to do is I need to go back to table B1 or table B2, and I need to find the heat capacity of benzene as a gas. And if from the table I get, and again, this is going to be a polynomial, so 0.07406. If you look at the table, what it tells us is that this first term is actually 74.06 times 10 to the minus 3. So make sure you practice reading the table so that we write these values correctly. Okay, this is going to be plus 32.95 times 10 to the minus 5t. I'm just going to scroll over this way so I can write all the terms. Then we have minus 25.2. Let me just go ahead and erase this right here. 25.2 times 10 to the minus 8 t squared plus 77.57 times 10 to the minus 12 t cubed. Okay, so this term right here is going to go inside this integral, and there's various ways you can do that. You can use software on your computer, you can integrate on your calculator, or you can integrate it by hand and plug the numbers in. That's going to be your choice. This first term right here, again, we're going to use the heat capacity of the liquid. So this is going to be 0.1265 times, what is it, 80.1 minus 25. This heat of vaporization term is what we have up there, 30.765. 765. Now note, let's just kind of do a quick unit check. This is kilojoules per mole degree C times degree C. This term right here is kilojoules per mole. And then we're going to have plus the integral of this term. I'm not going to rewrite it out. But again, the units on here are the same as the first heat capacity term. So the units should check. And this is going to give me my delta H2, which remember, delta H2 is going to be H2 minus H2 minus H ref. And because H ref is 0, this whole term is going to be our H2. And if we go ahead and do that calculation, I'm not going to spend the time to plug the numbers in here. We get what is this, 39.91. And then if we do the same thing for toluene, so delta H4, this is going to be, for toluene, it's going to be the heat capacity of toluene as a liquid, 0.1488. And then we're going to go to the boiling point, which is, for toluene, it's 110.62. So 110.62 minus 25. Plus, we're going to use the heat of vaporization for toluene, which is 33.47 kilojoules per mole. And then we're going to do the integral from the boiling point, which is 110.62 to the exit temperature, which is 95. CP toluene as a gas dt. And again, we can get this from table B2 also. I'm not going to write it down again. One of the things that I want to point out to you here is that we have to, our hypothetical path is increase the temperature of the liquid to 110.62, but this is higher than the temperature that it comes out, but that's okay. Then we use the heat of vaporization, and this heat of vaporization for toluene is at 110.62. And then we cool down the toluene vapor from the boiling point to 95, which is the exit. So note, this is going to be a negative value. So just make sure that if your boiling point is higher than the exit temperature, this term that you end up calculating is going to be negative. One mistake I often see people make is that they add this to the term, which makes it end up being a little bit higher. So if we go ahead and do that calculation, we get 46.06. Now for our final calculation, we want to calculate this right here. Let's do this. We're going to go calculate this because we said this term was 0 because the entering terms are 0. Now we're going to have the sum of NN times HN for each one of these terms right here. And if we go ahead and we calculate that, we will end up with a final Q. Oh, this isn't looking very neat. We will calculate a value of Q equals 2.3 times 10 to the 4 kilowatts. I want to note that if I didn't make the simplification for the heat capacity of the liquid, so if I use the extra temperature dependent term, I would have ended up getting a heating rate of 2.42 kilowatts. So or 2.2 times 10 to the 4 kilowatts. So I'm a little bit off, and the reason for that is because the temperature changes for the liquid is so high. Okay, but I want to now, the part B of the question says, use Raoult's law to check to see if these values make sense, the vapor and liquid composition. So part B says, use Raoult's law and see if these are consistent with the temperature, and then calculate what the operating pressure would be. And if it's not consistent, give some reasons why. So if I use Raoult's law, which is YB, so for benzene, YBP equals XB PB star of 95 degrees C, I can use Antoine to calculate this. And then I know these two mole fractions, so I can calculate pressure. If I calculate pressure from the benzene equation for Raoult's law and calculate pressure for the toluene equation for Raoult's law, I'll see that those pressures are not equal to each other. Therefore, Raoult's law, or therefore, this there's something going on here that's leading to this inaccuracy. And the reasons for that could be is that the analysis for these compositions given, either vapor or the liquid, are incorrect. Other reasons could be the system is not at steady state. And I don't know, you could maybe possibly suggest some other reasons that might be occurring. But that's all I'm going to do here. I'm going to stop there, and we'll see you on the next video.